Okay, looking at a couple of problems that are related to problems that weren't completely done correctly by some people on the homework. We have W equals the set of x, y, z such that x is negative 2. That is the set of vectors in R3 whose first coordinate is negative 2. We want to see if this is a subspace. Okay? Typical elements of the space, just to get a feel. Anything with a negative 2 for the first coordinate. Negative 2, 5, 7, negative 2, negative pi, negative square root of 12. In general, negative 2, y, z. Question is this set closed under addition, under vector addition? So let's just take two arbitrary members of the set. You got to have negative 2 for the first coordinate. Second and third coordinates could be anything. So we'll call the second and third coordinates here y1 and z1. Here we'll call the second and third coordinates y2 and z2. If we add these two, we get this. And you notice we've got a negative 4 in the first coordinate, as the first coordinate. And then we've got y1 plus y2, z1 plus z2. But this doesn't matter. As soon as we see the negative 4 as the first coordinate, we know that it's not in this set. So the set is not closed under addition. It's not closed under scalar multiplication either. And I just use the example. If we multiply this by any number except 1, we're not going to get negative 2 for the first coordinate. So if we multiply this vector by 3, we get negative 6, 3y, 3z. It's not in this set because the first coordinate is not negative 2 anymore. So it's not closed under addition. It's not closed under scalar multiplication. We can look at this geometrically. It might be a little hard to see this picture. But if the x-coordinate is negative 2, then in R3, here's x, here's y, here's z, here's negative 2, here's a line, x equals negative 2 in the xy plane, but every point above and below that also has x equal negative 2. So you have this whole plane sitting back 2 units on the x-axis. Intersecting the x-axis. It's a plane parallel to the yz plane, sitting 2 units back on the x-axis from the origin. Okay, now we can have a couple of vectors. We have a vector out to this point of the plane and a vector out to this point of the plane. If I add these two vectors, well, this vector is going to take me 2 units back from the origin. If I add this vector to this vector, it's going to take me 2 more units back from the origin. So it's not going to be in the plane anymore. And that's analogous to what I did here. If I double this vector, well, this vector takes me 2 units back. If I double it, it's going to take me 4 units back from the origin. It's not going to be on this plane. So neither adding 2 vectors from the plane nor multiplying a vector by any number but 1 is going to take us off the plane. If I multiply this vector by a negative number, it's going to bring it out on this side of the xy plane, or yz plane. So clearly, this plane, the set of vectors that go to this plane, and that set could be represented by this plane, they don't form a subspace. I'll mention that if we took, just say, these 2 vectors and did a plane that intersects both vectors, a plane that, in which both vectors, or both of the lines of these vectors starting at the origin, lie within the plane, then that plane would be a subspace, because if you add this vector to this vector, it's still going to be in that plane. So hopefully you've seen examples of that sort of thing. Okay. Now let's take another type of a problem. Problem is, write v equals 6, negative 1 is a linear combination of the vectors u and w, where u is 3, 1, w is 3, negative 2. To write these this is a linear combination, you got to find a C1 and a C2 such that V equals C1U plus C2W. Okay, in other words, here's your linear combination of these vectors, got to equal this vector V. We write out the details of what this means, substituting 3, 1 for U and 3, negative 2 for W. We get this equation. Multiplying through by C1 and C2, we get this and this. I'm not going to read it to you, it's clear. We get 6, negative 1 equals this sum. Well, if we add these two vectors, we get this. And now we know that 6 has to equal 3C1 plus 3C2. Negative 1 has to equal C1 minus 2C2. That's two simultaneous equations. 3C1 plus 3C2 equals 6. This equals this. C1 minus 2C2 equals negative 1. This equals this. This is equivalent to the vector equation, or the matrix equation, 3, 3, 1, negative 2 times the C1, C2 vector equals a 6, negative 1 vector. This then can be written as AX equals B, so that X equals A inverse B, provided this vector is this matrix is invertible. Well, the determinant of this matrix is negative 6 and negative 3, negative 9. It's certainly not 0. So this matrix is invertible, so we have a solution. Now, I haven't found the solution. That's pretty easy, excuse me, to invert a 2 by 2 matrix. We can do that, multiply by 6, negative 1, and find the C1 and C2. So I haven't done that step. That I would leave to you, but there it is. Okay, now we go on and we do kind of an example of this with vectors in R3.